Hello everyone and welcome back once again. So we have been discussing about homogeneous and heterogeneous nucleation in relation to grain refinement during solidification. So we will continue on this topic in this lecture today and learn about the other aspects of melt inoculation. Okay, so if you keep the system at the melting point when you are talking about this transformation between liquid to solid or solidification, it is going to reach an equilibrium because the solid might form, but there is the latent heat of fusion which is being released, right? So it will try and reach an equilibrium and there will be no driving force for the solidification to continue. And you can also see it from here that right at the melting point, delta G is 0, right? So we do not have the driving force for the solidification to continue. Only when you reduce the temperature below the melting point, the solid will start to form, right? So the actual solidification starts at a temperature T, which is below the equilibrium melting point, and this difference, delta T, is known as the undercooling. And it can be shown that this free energy change delta GV is actually equal to this. So it is basically proportional to this undercooling. Wherein delta HM is the latent heat of fusion. Right? So from here you can realize that as the undercooling increases, delta GV also increases. And what is its significance in terms of the nucleation process? That you can see if you again bring these two equations over here, that is the expressions for the critical size and for the energy barrier, right? Or delta G star. So you can see from here that as delta GV increases, both of these parameters decrease, R star as well as delta G star. So what that essentially means is it is easier to form the nucleus because the size reduces, the critical size reduces, so the nucleus can be stable even at lower size, and the energy barrier also reduces, okay, both of which will actually facilitate formation of the nucleus, right? So it means that as you increase the undercooling, the nucleation rate will increase because when you increase the undercooling, delta GV also increases and it becomes easier for the nuclei to form, right? So higher delta T means higher nucleation also. And you may also know that a high cooling rate promotes a high undercooling. And therefore, we can say that a high cooling rate will lead to a high nucleation rate. And this provides you one more method of grain refinement by high cooling or rapid cooling during solidification. Right. So apart from addition of grain refiners into the melt, we have another technique by which the grain size can be refined during the solidification process, and it is through applying a high cooling rate, because as we have seen by now, a high cooling rate will promote a high undercooling, and that will in turn lead to a high nucleation rate. And we know by now high nucleation rate means a finer grain size. Okay. So I think we are now done with setting the background for this grain refinement technique during solidification. Right. So what we have seen in the previous class, if you can provide a heterogeneous surface in terms of some solid particles which will remain solid in the liquid phase of the parent material, then you can actually increase the nucleation rate and refine the grain size. Right? And this is what is done in this process known as melt inoculation. This is basically addition of those grain refiners into the liquid metal for promoting heterogeneous nucleation to refine the grain size. Okay, and that is what we are going to discuss next. The most commonly used melt inoculant for aluminium and its alloy is titanium. Titanium has a much higher melting point compared to aluminium, so you can expect titanium to remain as solid suspended particles in the aluminium melt. But it is not the metallic titanium which plays that role. It is rather this intermetallic which forms between aluminium titanium, which will act as those suspended solid particles, providing that heterogeneous surface for the nucleation. Okay, and this is actually added in the form of aluminium titanium master alloys having a certain percentage of titanium. So talking about grain refiners, we can have different types. Most commonly used are these. In terms of the elements, if you see, for aluminium, these are the most commonly used grain refiners. And out of all this, titanium has been found to be most effective. And that is why this is the most commonly used grain refiner. As I said before, it is used in the form of aluminium titanium master alloys. But if you can have another element along with this, that means instead of these binary master alloys, if you could have a ternary one having one more element added to it, for example, aluminium, titanium, boron, then it can provide you some additional surfaces for the nucleation in the form of these TiB2 particles, which will come in addition to L3Ti. Okay. So now that you have both of these particles, you can expect a higher nucleation rate or more effective nucleation. And as a result of that, you can expect the ternary alloys to be more effective compared to the binary ones. Okay. But nevertheless, you can also use aluminium, titanium binary alloys as well as the grain refiners. And in that case, the typical compositions, if you see, or the amount of titanium which is actually needed for the grain refinement to occur is very small. For example, 0.01% titanium is enough for generating those heterogeneous nucleating surfaces in the form of these intermetallic particles. Okay. So if you talk about adding this in the form of a master alloy, such as aluminium, 5% titanium, and some amount of boron, let's say 1% boron, then you need only 0.2% of this, right? Because here titanium is 5%, you need only 0.01%. So 0.2% of this aluminium, 5 titanium, 1 boron master alloy is enough as a grain refiner. Okay. But sometime you can also add little higher quantity, let's say 0.05% titanium, which can be added in the form of aluminium 5 titanium master alloy. So for this alloy, you would only need 1% for this 0.05% titanium that you need in the melt. Okay. So typically about 0.01% titanium and 0.003% boron is used for most of the grain refiners, and the other factor which plays a role is the titanium to boron ratio. So TIB ratio of 5 and 3 are commonly used. And apart from that, you need to also look at the other factors, particularly the reaction temperature and the time. So here you add the grain refiner to the melt, and you need to allow certain time, right? Certain time for these particles to be generated, and then for them to act as those heterogeneous sites. Okay, so that time has to be allowed, and at what temperature you are performing all this, that would also affect. Okay, so the reaction temperature and time have to be considered for this grain refinement. And then you also have to look at what is the cooling rate. Because this can affect the morphology of those intermetallic particles which are acting as the heterogeneous nucleation sites. For example, if you rapidly cool from high temperature, petal-like aluminides will be generated. Okay, the intermetallic particles will have a shape like, a morphology like petals. Okay. On the other hand, slow cooling from high temperature will lead to plate-like morphology. And then the temperature will also have an influence. So if you do this slow cooling from lower temperature, then the morphology will change from plate-like to blocky type. And generally, if you have high temperature, you can expect a circular kind of morphology for the intermetallic particles, the aluminides, and for low temperature, it will be equiaxed. So this transformation to the equiaxed kind of morphology, from the acicular or needle or plate-like kind of morphologies is actually attributed to a change in the interfacial energy with temperature. Which restricts the growth of the particles in limited number of directions, and therefore it turns into this kind of morphology. We'll discuss a little more on this morphology as to what is the actual influence of this on the grain refinement efficiency. As we proceed, we are going to discuss that as well. So if you talk about this Al3Ti particles, that is the titanium based grain refiners, these particles are generally faceted and therefore the number of faces or number of facets on which aluminium can form will be more in a particular type of morphology, right? So depending on the facets that the morphology or the number of facets that a particular morphology can offer, the efficiency of the grain refinement will change, right? For example, if you talk about a blocky kind of shape, the number of facets which can be offered for the nucleation of aluminium is more. Compared to a plate-like morphology. And why is this so? Because for the heterogeneous nucleation to occur, the heterogeneous surface has to provide some planes on which there is little mismatch in terms of the orientation between the aluminium and this surface and the nucleating surface. So there has to be some planes which can provide a minimum disk registry. So it has to provide certain planes, which will have some orientation relationship with the planes of aluminium. And such planes having the orientation relationship with aluminium will be more favorable for the aluminium to form, which is obvious. And therefore, if you have morphologies which can provide such surfaces, by having more number of facets, it will be better as a nucleating surface. For example, the two planes of Al3Ti have low or little mismatch with one planes of aluminium. Right, so such planes of Al3Ti will then be more efficient in terms of nucleating the aluminium, because here the dysregistry is low, the mismatch is low, and therefore aluminium can easily attach onto the surface or this kind of planes of Al3Ti. Okay, so that is where you can see the effect of the morphology change on the efficiency of grain refinement, although it may be the same particle or it can be also a different type of particle altogether. For example, if you add the other elements such as boron, you will have TiB2 particles. So apart from the particle itself, you also have to look at what kind of surface or plane it can provide to the aluminium for the nucleation to occur. Okay, whether it will have this kind of planes of low dysregistry having certain orientation relationship with the parent material, that also has to be looked at. Okay, right. So these are the different aspects of the grain refinement by melt nucleation, and from now on we'll also have to look at the actual mechanisms by which this occurs. We'll have to see how exactly the heterogeneous nucleation takes place on these kind of particles and how it leads to grain refinement. Okay, so that is what we are going to discuss next. But for now, this is all I have. So I'll stop here today, but I'll see you soon again. Thank you.